ICCS Journal Club. I'll start that again. Welcome to the ICCS Journal Club for October 2025. This month we have two speakers from the Institute of Computing for Climate Science who are highlighting a unique strength we have as a centre as we do collaborate with all six of the VESRI teams. That gives us a broad view of the research and the software efforts that are going on in this space, and that allows us to identify and develop cross-cutting concerns. And today's talk is an example of one of those. Speakers, Jack Atkinson is a senior RSE in the ICCS, and he has a PhD in fluid mechanics. Worked as a postdoc studying volcanoes and worked at the British Antarctic Survey in space weather before coming to the ICCS. He is a 2025 Software Sustainability Institute Fellow. With us today also is Joe Wallwark, who is also a senior RSE in the ICCS. He has a PhD from the Mathematics of Planet Earth Centre for Doctoral Training, and he has worked as a postdoc at Imperial College London and at the UK Met Office. Software he has worked on includes PETC and the UK Chemistry and Aerosols model. So, Jack and Joe, the floor is yours. Take it away.
Super, thank you, Chris. So yeah, I feel there's not much more to say, but yeah, we're going to talk to you a little bit today about some software we've been developing at ICCS called FTorch. And this is mainly with the view to kind of facilitating hybrid modeling, which is one of the big focuses of the VESRI projects and many, many other projects besides at the moment. So I've put a link to the slides in the chat. And so if people want to go and follow the links there, then you can do. And if you want to refer back to them later, they should stay online. So kind of the motivation for this work, I don't think needs selling too much to people, but just in case, sort of we deal with these large weather and climate models, particularly numerical models running on high performance computing systems. And typically these are running with some kind of sort of central dynamic core that captures kind of large scale flows around in the planet. But then sort of to make these more accurate or more realistic, we have a series of sort of sub-models to represent various other things, for example, microphysics or radiation, convection, that sort of go alongside this. So these sort of parameterizations are often representing processes at what we call the subgrid level. So if we think of our computational model dividing things up into a mesh and those boxes being of the order, I don't know, of 100 kilometers by 100 kilometers, obviously there's a lot of things that are going on at processes smaller than that we can't capture with the numerics. So we have to have some kind of other model to represent them. And this is what we call parameterization. And sort of this goes even further down below the grid boxes to sort of the cloud level. We can never capture this behavior. However, it's sort of these processes or these subgrid models that often tend to be one of the largest sources of uncertainty within these large climate or atmosphere ocean models. And so they're also kind of a very good target for application of new machine learning techniques. So on the subject of machine learning, sort of traditionally, I guess we would think of this as being an end-to-end process, particularly from kind of the early days of machine learning, where you had some kind of input, you churned it through some machine learning approach, and you got some kind of output. And this, I guess, is if you think a little bit about those weather models, such as, the AI weather models like GraphCast or Pangu, these operated on a similar principle where you kind of took your inputs, you put it through a big ML model, and you got the outputs. But that's sort of not where we're interested with this work. So we're talking more about the idea of hybrid modeling, by which I mean we retain most of our large numerical model, and we just replace kind of one small part of it, say the convection parameterization, with some kind of machine learned scheme that we hope is going to give us sort of more accuracy or better computational performance than the sort of the traditional subgrid model. So that's the realm within which we're working. Doing this, however, brings sort of a series of challenges that we have to think about from both scientific and the technical perspective. So one is kind of the reproducibility aspect. So if you've often sort of trained this machine learning component on its own, just focusing specifically on, say, convection or focusing specifically on radiation, you want to be sure that it's still functioning in the same way when you embed it back into your large model. There's also some reusability built in there. So we want kind of these parameterizations that we develop to be easily applicable to many, many different models and sort of portable between if possible. And we also want it to be easy to kind of retrain them or adapt them to sort of further improve them as we continue. And the big challenge that we're going to talk about most today is the one of language interoperation. So if we think sort of think about traditional ways of doing either end of this, a lot of our big weather models or climate models are being written in Fortran, sort of compiled language, array-based, heavily optimized to run on high-performance computing systems and with huge code bases. Conversely, a lot of the machine learning that people are doing is written in Python, PyTorch or TensorFlow. I think science moving more on the PyTorch end of things these days. And that's because there's sort of lots of very good frameworks that give you lots of options and opportunities to do different and exciting things in these frameworks. But there's a problem if you've developed some code in Python with machine learned parameterization, how do you then run it within the Fortran? And particularly, how do you do so in a sort of computationally efficient manner, but also in a way that you can remain focusing on kind of the science and not get bogged down in sort of the technical implementations. So there's a few possible solutions that are out there. So one option would be to implement your neural net in Fortran. However, we would generally discourage this because whilst perhaps simple feed-forward nets are a series of matrix multiplications, there's still, you're kind of doing work a second time, and it's also going to be additional work on you kind of ensuring that you're testing to make sure you're getting bit for bit sort of reproducibility between the two systems. And more to the point, sort of we're moving more and more towards more complex neural net architectures these days. And whilst the feed-forward nets is quite straightforward, it's going to be much more difficult to implement these. So one option, again, is there's a kind of a nice template script, and a lot of the early efforts in this domain made use of this called 4Py. So it's quite easy to add to your project. It's just the Fortran module that you drop in. But there are some difficulties with using it with kind of machine learning frameworks. It's designed mostly just to give interoperability between sort of numbers in and out. And it's also sort of barely maintained. I think it's been a few years now since there are any updates or bug fixes to this. And then so we've also got SmartSim. So this is developed by Keras, or at least it was. I think it's on a bit of a back burner now. And sorry, developed by HPE, I should have said, not Keras. And this is sort of provides a control center around simulations. And so you sort of read and write data via the Redis API into a database and sort of communicate between the two programs. And so this is kind of a very nice control center, particularly if you're running lots of ensemble simulations. But there's quite a steep learning curve, and there's sort of a lot of infrastructure to put in place if you're just looking to implement one model in your simulation. And finally, there's the Fortran Keras bridge, which deals with TensorFlow, but I think this at this point could be regarded as abandonware. So there's also, I think, following on from this, sort of two important considerations which really underpin a lot of the project we've got here. And this is about sort of the efficiency, particularly of the audience we're targeting. So there's computational efficiency, which we're probably quite familiar with. We want our code to run fast. We want it to not utilize excessive amounts of memory, sort of do sensible data transfer. But within science, particularly within research, there's also, I think, what we have to regard as the developer efficiency. So again, bearing in mind that sort of a lot of people perhaps trying to do this, PhD students, postdocs, won't necessarily be trained in the deeper levels of how you build and run a climate model, how you link things, how you couple different libraries together. So if we can reduce that barrier to make it really, really easy for people, then it's actually going to allow time for a lot more science to be done and a lot more sort of things to be investigated. With that, I think I'm handing over to Joe at this point.
Yes, that's right. Let me just try and share the right thing. Okay, hopefully you can see this, my version of the slides.
Hard to tell. Are they exactly the same as Jack's version?
They are, yeah. Yeah.
Okay.
Thank you. Yeah, so we're going to, I'll talk a bit more about this sort of the details of FTorch now that Jack's sort of given us the motivation behind it. So our approach, as you might guess from the name, is related to PyTorch. So PyTorch has a C++ backend. So most people interface with it in Python, but it's got the C++ backend called libtorch. And there's an API that's provided for that. So our approach in FTorch is to bind from Fortran to C using ISO-C binding, which has been part of the Fortran standard since 2003. And what we'll do is save PyTorch models into a portable torch script format, which can be run using this libtorch C++ API. So the idea is that in this sort of standard workflow that people have been doing up until recently, you would still write your model in Python, because that's sort of the natural way to design these machine learning models. And then you can save it in this torch script format, and then that can be loaded in FTorch. So we provide the Fortran API to do that, which wraps the libtorch C++ API, and it abstracts away the complex details from the users so that they don't need to know anything about language interoperation. So we can consider here, this could be sort of thought of something similar to the 4Py approach that was mentioned before. So PyTorch is usually used in Python, and so one approach could be to communicate between Fortran and a Python runtime. That's what 4Py would do. So there would be a Python runtime which would be sort of connected to your Fortran code, and you could transfer data between the two. But this starts to become quite problematic, especially when you're running on HPC, because having this reliance on the Python runtime can be sort of problematic just in terms of setting it all up. But it can also have performance bottlenecks as well. So what we do instead is, as mentioned on the previous slides, go directly from Fortran to the underpinning code for PyTorch. So you can find, there's a QR code there and a link to the FTorch GitHub repository. And I'll just go through a few of the highlights. So it's very easy to clone and install. We use CMake, and it's supported on Linux, Unix, and Windows. And you can also link it using CMake or with GNU-make using the flags that I mentioned just below. We're sort of work in progress as well. We're looking at sort of packaging for this. So we've already packaged FTorch with Conda, and that works sort of out of the box. And we've got work in progress setting it up with SPAC and also with FPM as well, the Fortran package manager. So hopefully, with one of these many approaches, you'll be able to install FTorch in the way that you'd like to. We also provide some user tools in addition to the sort of core library. So everything we've mentioned so far is about wrapping the PyTorch functionality. We also have this script that's called PT to TS, which is PyTorch to Torch script. So it will convert your PyTorch models, which typically have a .pt extension, into this Torch script portable format that can be read by FTorch. We've got quite a large suite of examples now that go from very, very simple sort of demonstration of how to operate on tensors all the way through to sort of more advanced architectures. So hopefully that's enough to sort of get you up to speed with whatever it is you want to do with FTorch. We have full API documentation for all of the subroutines, data structures that are inside FTorch, which you can see on the web page. The URL shown below. And it's free and open source. licensed under the MIT license. So it's very permissive. Up until recently, pretty much all of the contributions to FTorch have come from within Cambridge RSC teams. But recently we have started to have a few external collaborators, which we're very excited about, and we would be very happy to welcome other contributions from anyone that's interested in contributing to FTorch. Some highlights on the computation side. So we use the framework's implementations directly, that is PyTorch. So the feature and future support is and also reproducibility is ensured by that. So as you know, machine learning technologies is quickly advancing, as Jack said, and if we were to re-implement all of these different things in Fortran, then we would have to keep updating our code as new machine learning approaches appear. But given that PyTorch is quite a well-established package now, the fact that we sort of piggybacking off of it means that we can keep up to date with these advances. We make use of the Torch backends for GPU offloading. So we have supported CUDA GPU for quite a while, and then in more recent times have extended support for HIP, which is for AMD GPUs, MPS, which is for Apple Silicon, so the kind of GPU that you would have in a MacBook, for example, and then also XPU, which is for Intel GPUs. So there's still a few other ones that are supported by PyTorch that we could add, but this covers quite a large sort of proportion of the GPUs that people are using, out of the people that we work with. But if there's one that you would like us to consider, then we'd be very happy to look into that, or would be happy to accept pull requests to add it in. So you might be thinking, well, Fortran uses different index ordering than C++ and Python, so how does that work? Well, we sort of handle all of that for you. So by default, it will do the reshape that is required to go between the row and column ordering. If you really want to, you can provide your own stride to have greater control, but by default, it will just sort of do the thing that you might expect. Of course, it causes some headaches for us as developers, but for the users, it shouldn't cause any headaches, which is good. Also, there's a no copy access to the memory, at least on CPU. So we'll show a diagram for that. So you have your Fortran array. So this is shown on the left-hand side in the purple box. It's just a standard Fortran array. And then we provide some syntax for the wrapper for the PyTorch tensor. So we have these FTorch tensors, which they wrap all of the functionality that is associated with the PyTorch tensor, and then they also have a pointer to this Fortran array. So because we use a pointer, the same array that we are operating on in Fortran is the same as the data that's being handled in C++. So if you edit your Fortran array, it will also edit the data associated with the PyTorch tensor and vice versa. So the really nice thing about this is that there's no cost for data copying because there is no data copy. We're just operating on the same data. And this is different from some of the other approaches that were mentioned earlier where data copying is required. Of course, there is a caveat on the GPU because in many cases, you have to do a copy to go between the CPU and the GPU. Possibly this would still work on if you have a shared memory space. I'm not sure if we've sort of experimented with that enough to say for sure, though. So I believe at this point, I will pass back to Jack.
Yeah, thank you very much, Joe. And yeah, I guess if anyone has a Grace hopper that they would offer us to have a play around or want to have a play around, we're all ears. So yeah, at this point, I'm going to talk a bit about, or take a look at kind of some of the code, hopping back to sort of this idea of wanting it to be as easy as possible for people to bring this into their models and get using it to do science. So starting off with saving models from Python. So if you've created your neural net, run through, sort of done your training, and you've got that PyTorch representation, then there's a series of functions that PyTorch provides under this sort of JIT extension or JIT operator that will take that model that you've got and save it out into Torch script that I think Joe mentioned earlier. So a little bit more on what Torch script is. It's kind of this statically typed subset of Python, so it makes it sort of slightly easier to be read in by the C++ interface. And it provides sort of an intermediate representation of the neural net, including any weights and biases that you've trained sort of all saved up into that one blob. And there's two ways of saving this. You can do it by either sort of tracing operations through your network, which can be a little bit faster, or if you've got sort of conditional code where you need to be much more rigorous about capturing that architecture, you can use what's called the JIT scripting functionality. And this will save it to sort of a blob representation of your neural net with all the information in there that you need to then read and run it from either the C++ in libtorch or indeed from FTorch. So once you've done that, so going through sort of those, it's there. And so this will save your model out to this file. So once you've got that file saved in Torch script, we can move to look at implementing this within a piece of Fortran. So the first part of this is to import FTorch using sort of Fortran's use statement. And again, sort of we've designed this to be familiar in the way you would sort of approach using netcdf or MPI, bring it in at the top. The next step is, as Joe mentioned previously, we want to create our torch tensors and map those to some input data. So this is assuming we've still got that in data and out data are arrays within the Fortran. We then have sort of these dummy types called torch tensors. And then there's an operation torch tense from array, which is saying, take this sort of dummy type or this tensor type and actually attach it to my Fortran data that I've got that already exists, and specify also here that it's this is an array that's sitting on the GPU. Once you've created the tensors, it's a case of loading a model to put them through. So again, there's this sort of type that we've created, which is a pointer underneath, which is the torch model. And there's a handy function we provided, which is torch load model, which you can give it the path to the torch script file that you saved in the previous step with the Python, and it'll read it in, load it to memory, and store it there. And again, we're specifying that this sits on the CPU. The next stage is the torch model forward. So hopefully people can probably guess what this is going to do. We give it the net that we've loaded, the tensors that we've got as inputs, and then also the tensors that we want the outputs to be written to. So this is sort of slightly different from the Python because we're in Fortran, so we have to pre-declare those outputs. But running this will take those inputs, run them through the net, generate the outputs, and deposit them in the data. And I say deposit them in the data because there's then no further sort of operations that are needed to extract them from the PyTorch. Because we've got this shared memory, they're immediately available for use in your Fortran going forward. Again, sort of one final slight nuance here is that because this is Fortran, not Python, there's a little bit of cleaning up that it's sort of good practice to do at the end of this to clear our memory space. And then hinted at this slightly before, but as Joe said, we've got GPU accelerators there as well, sort of piggybacking off the implementations within PyTorch. And this allows us to do operations utilizing these accelerators from within Fortran. To do that, it's a case of when you declare your torch tensors and then attach the data from Fortran to that torch tensor, rather than specifying the CPU, we're now specifying the torch CUDA device or HIP XPU MPS, as you wish. And another thing to highlight here is that we also include support for multiple devices if you're lucky to have more than one. So there is the option here to send different workloads to sort of different devices within one node. The other note here is that, as Joe mentioned, there is going to be some data overhead transfer if you're needing to move data from a CPU to a GPU. And so doing sort of efficient simulations on the HPC is probably going to require some form of MPI gather to make sure that we're gathering enough data into a chunk before we send it to a GPU so that we don't sort of end up throttling there. And oh yeah, and then the same for declaring the device for the model as well. Hopefully that gives a bit of an overview. I would say that exciting news at the start of this year is that we had a publication accepted into JOSS, the Journal of Open Source Software. So you can find this at the linked DOI. And yeah, if you're using FTorch in your work, or if your collaborators using it, we very much appreciate if you can cite us sort of at this source as a definitive source. The other thing to mention is that as well as providing sort of really comprehensive examples in the FTorch repository, kind of taking people step by step through how they would set up and use FTorch in their work for a variety of different applications. There's also kind of an online workshop that we've been delivered a few times, and this runs in GitHub Codespaces. So if you want to have a bit more of a play there, you can go and check that out at the linked repository. Moving on, I think I wanted to talk a little bit about some sort of applications and case studies from FTorch that we've had with both collaborators from the Vesri space, but also further afield. And so I should say the first place to start, I think, is with MIMA, which was a data wave project. And I'll give a quick tour here, but Joe did a really good talk at RSECon recently talking about how FTorch began as kind of a solution for one individual project, which was MIMA with DataWave, but actually by recognizing the benefits that this could have in sort of projects with several other Vesri partners or further afield, and realizing that sort of the solution here could be wrapped up and sort of made more general, we actually sort of made a lot of efforts to do that and provide this kind of standalone library that eventually has become FTorch. So here was sort of early parameterizations, particularly for gravity waves and coupling to an atmospheric model using 4Py, the library I mentioned previously. But because this was going out and calling the Python runtime every time it wanted to run the neural net, it was becoming prohibitively slow. So whilst it was kind of scientifically correct, computationally, it was onto a loser. And so we were approached by DataWave to see if there was a way of speeding this up and making it sort of making it more computationally efficient, but also with sort of the view that this might be something that's was used in further studies. And so this is what we did. And indeed, there were a few follow-up papers, or a follow-up paper here from Laura Mansfield, who's now at Oxford, who took the work we did sort of implementing one neural net within the MIMA atmospheric model, but actually explored using a range of different nets, all trained on identical data with identical architectures, but with different random seeds. And interestingly showing that even though they had very, very similar performance offline, when you deploy these online, you get sort of a wide variety of behaviors with sort of the model moving into different regimes depending on which particular net was employed. And this has sort of gone on to be sort of a thing Laura's looking at quite a lot with model uncertainty in this area. So the second place I wanted to talk about was deployment in ICON. So this is the weather model used by the German Weather Service, ICON for icosahedral for the mesh structure. And this was a study that came from Hoyer et al. In 2023. So here, what they did was sort of trained a UNet on for convection before embedding it back into a high-resolution simulation. And they deployed this in ICON, again, using FTorch. The interesting thing I think about this paper was that sort of scientifically, they showed that whilst you could get very, very good offline performance by throwing sort of every bit of data that you have at the model, when you put it online, you start to get some very, very spurious behavior starting to occur, particularly with sort of instabilities. And they showed that actually, if you look at the SHAP values, look at the net you're training, and remove sort of some of those causal relations, for example, predicting convection based on updrafts when updraft is maybe a diagnostic, then actually you significantly improve the stability when you're running it online. The other reason sort of this was a particularly exciting project for us to see is that we only heard about it when it reached publication. So it was something that we hadn't had any involvement with, but sort of was a nice feather in the cap to show that FTorch and the documentation and examples that went along with it were allowing other researchers to deploy it in science and get science done sort of without lots of hands-on supervision from us. And indeed, this has sort of been built up following that study, such that ICON, sort of the hybrid model of ICON, is now looking to employ an interface for several different schemes based around FTorch. So these are slides from Julien Savray from our recent hybrid modeling workshop here in Cambridge, where he was talking a little bit about this. Okay, another sort of project we've had within the VESRI space is looking at bringing coupling into the community Earth system model. So again, this was sort of motivated by this idea of trying to make it as easy as possible for those who are working with the CESM model, and particularly the associated components, make it as easy as possible for them to be employing machine learning within their work without needing to worry about building a software stack behind it, implementing some kind of coupling. Ideally, sort of FTorch would just be there, ready for them to go, and anyone could grab it when they wanted to interface a PyTorch neural net. And this is some work that we've been doing with Will Chapman, who's over in, was over in NCAR, I think has recently moved, but sort of with the CSM team over there. So there's a range of other papers that sort of have come out since citing FTorch, a selection of which I've got here, which we don't have time to sort of delve into all of them, but I should mention the sort of the second one on the left there is the work that that Will was doing. And I've also highlighted in this list sort of the range of different models that we're working with. So we've got some that are coming out from the Met Office, we've got those from NCAR, others from NOAA, but sort of quite a range where people have been able to deploy this to do work in a number of different places. And with that, I think I'm passing back over to Joe to talk about sort of some of the exciting new features where we think we're going to next.
Thanks, Jack. Yeah, so I'm going to talk a bit about online training and AutoGrad, which are things that we've been working on earlier this year. So up until now, FTorch has been focused on enabling users to run models that are trained offline. So I mentioned this earlier on. So what we mean by training offline here is that you implement your machine learning model in PyTorch, Python. You get some training data, which you've probably written out from a Fortran model, but in either case, you've written it to a file. And then you have your training loop that's done written in Python. This is kind of the standard approach. So you'll have some training data, you'll do your training in Python, and then once the model has been trained, you'll save that to file and then load it in Fortran and use it for your inference. So that's sort of the workflow that we've been referring to so far in this talk. But with following some discussions with collaborators, it became apparent that this isn't always sufficient. So in some cases, whilst the offline performance is very good and the loss curves descend as you would like, and you get very nice results based on your training data, when you plug it in, you don't necessarily get the results that you expect. And in some cases, the model can be unstable. So one way that you could get around this is by having a pre-trained model that you've done in this way, but then being able to fine-tune the model based on data that it sees as you're running the model. So this is sort of moving towards a sort of online training approach where you're doing the training on the Fortran side as well. So being able to potentially account for some errors that are being accumulated as an output from your machine learning model, and then using that to feedback and train the thing. also, so related to online training, all of this training effectively is doing back propagation on the neural network. So it's automatic differentiation. You have an output, and you want to compute the sensitivity of the output with respect to the control variables, and the control variables here are the in the case of a neural network, it's the weights that you have in that network. And so this fits quite nicely with the concept of differentiable models, which are becoming increasingly sort of popular in the weather and climate domain. So where you can not only differentiate through the machine learning components of your model, but also other parts as well. So, thinking about these ideas of online training made us think, well, what if we could extend the notion of differentiability outside of the machine learning component into your sort of Fortran code? And again, earlier Jack mentioned hybrid models, so this all fits quite nicely with this idea of having different machine learning components. You can train them together and sort of stitch those bits together with some differentiable code. So it's a very nice idea, and there's a few pros, one of which is that you can potentially save large volumes of training data. So as I mentioned before, in the standard offline approach, you would save a load of data to a file and then use that for training. But in some cases, that data is not particularly useful for anything else. So you could just instead do your training on the fly and never have to write this data to disk or worrying about storing it. Another benefit is that it means we don't need to write that. Well, because we don't need to write that data out, we don't need to worry about the difference between how it's going to be written in Fortran and how it's going to be read in Python, which, as we mentioned earlier, there is this transposing that you would need to account for. Now, if you just use something like NetCDF, then this isn't too much of a problem. But if you do online training, then you're just working directly with the Fortran arrays. So there's not really anything to be concerned about there. And then there's also this possibility to sort of expand the concept of the loss function, which I'm going to talk about on the next slide. But it sort of means that we can potentially actually get a smaller error than we would have done just by using the sort of offline training model. So hopefully that'll become clear on the next slide. But sort of the main reason that people aren't doing this is that it's quite hard to implement, as you can potentially imagine. So this is something that we wanted to enable people to do with their Fortran codes and their PyTorch models. So just to come back to this idea of an expanded loss function. So we have typically loss functions are defined in the PyTorch code, and it's some kind of comparison between the output that you get and the expected output, for example. But what if we want to do something that's a bit more interesting? So you have a loss function that involves some downstream model code. So you have UML here is the output from the machine learning model, and it depends on parameters theta, which is the sort of the weights in the case of a neural network. And I suppose we also have U, which is the solution from the physical model that doesn't have machine learning. So if you're running the two of them side by side, you could make a comparison between the outputs in a way that's potentially more meaningful for your application. So I think if you were just to take those outputs directly and compare them, that wouldn't really gain you very much, because you could have just implemented that in PyTorch anyway. But I'm more thinking about cases where there's some kind of diagnostic or something that you want to be able to compute and then check the errors in that, for example. Or you could have some kind of error estimator. There's potentially quite a few options for things that people could do with this. But then, as I was mentioning before, if you want to be able to do training involving that loss function, you need to be able to differentiate through all of the components. And for this reason, we needed to expose the sort of autograd functionality, which is the automatic differentiation engine within PyTorch, into FTorch. The way that we did this was through implementing the requires grad argument. So this, if you sort of recall some PyTorch code, you need to give things requires grad in order to differentiate, well, if they're going to be involved in a differentiation. And then there's this backward method, which is what you call to sort of start the training. We also needed to overload some mathematical operators. So this is not an exhaustive list. We could sort of overload way more than this. But this was sort of a nice sort of set of operations to get started with, because with this combination of the sort of standard elementary mathematical operators, you could implement some quite interesting loss functions, as we'll show in a second. So this is a snippet of code here. It's, I've tried to keep it as minimal as possible for doing some very trivial multiple-step differentiation in FTorch. So we start off by creating the some tensors. So you can see technically here there's a tensor A and a tensor B, and they're associated with Fortran arrays, which have just been sort of hard-coded there. But you could also have this as a separate array so that you can query both the Fortran array and the torch tensor. But we associate these torch tensors with these arrays. We define them on the CPU, and then, as I mentioned before, we've got this requires grad because we need to use that if we're going to be doing some differentiation. I won't go through all the details, but effectively you can then do mathematical operations on these tensors. So there's just here a cubed minus b times b over some divisor, all multiplied by some scalar. It's fairly arbitrary. And then we've wrapped this torch tensor backwards. So we want to compute dq by dA and dq by dB is the idea here. So that will do the backpropagation, and then we can extract those gradients using the torch tensor get gradient. And this example is included in FTorch as well, if you wanted to give it a try. And then the final piece to do the online training is also to have the optimizers as well, because this is what the sort of engine that runs the training. So currently we've exposed stochastic gradient descent and Adam, and then the methods that are associated with those. And even just that on its own enables you to do some quite interesting things in FTorch. And then in terms of loss functions, there's quite a lot of loss functions implemented in PyTorch, and we haven't gone through and exposed any of the built-in ones yet, but we've implemented torch tensor sum and torch tensor mean because those are kind of sufficient to do some cases. And to sort of show that it all works, we've got a simple example. It's a fairly contrived example. It's just suppose that we have a function which has it's a vector of 4 components, f1 to f4, and we're doing a computation where there's a times x, where it's just a sort of point entry-wise product of 2 vectors, basically. And so if we start from the value 1, 1, 1, 1, and then we have a right-hand side of 1, 2, 3, 4, then effectively what we want to do is we want to minimize the loss function that means that f of x equals b. It's like a sort of least squares type thing. And so with this very simple example, we know what the solution needs to be. It needs to be 1, 2, 3, 4, because then you scale that by 1, 1, 1, 1, you get the right-hand side. And just to prove that it does, we've got a plot here where it's got the 2 different results with a PyTorch implementation and an FTorch implementation that give exactly the same results, which you can't hope, because at the end of the day, FTorch is a wrapper for PyTorch, so it would be concerning if this wasn't true, but it's it does do. And this work is being used in a case study that we're working on at the minute. So UKCA is the UK's chemistry and aerosol model, and it's used by the Met Office, and it's also used in the UK Earth System model. And it's the sort of chemistry component of it has a solver that's rather expensive, and there's a lot of interest in trying to reduce the computational cost of this chemistry solver. And one of the things that we've been investigating is the fact that there's quite a lot of redundant calculation that goes on. So for each time subinterval that we want to integrate, so like, you want to integrate from one time step to the next, you give it take a default time step of 1 hour, and then try to integrate with that step size. And in many cases that works, but in some cases it doesn't work because the chemistry is too complex or something. So you need to reduce the time step and try again. And so in areas, for example, certain points in altitude, and then certain points over like a mega city or something where there's very complex chemistry because of the pollution, you'll need to half the solver, half the time step several times in order to get it to work. And so there's some redundant calculation here, because in those cases, if we had an idea of how hard the problem was based on this sort of input data that we had, then we could just choose a smaller time step to start off with and not do these sort of attempted calculations. So this is sort of the use case here, that we're using this FTorch with online training, is to sort of predict this time step in advance. And one of the nice things about this is that we're not replacing any of the actual solver with machine learning. So it's not a sort of data-driven solver. It's just a sort of data-driven discretization. So it's a very safe use of machine learning, because if you choose a time step that's still too big, then it will just fall back on the original logic. And if you choose one that's too small, then you might end up getting slightly different answers, but it should still give a reasonable result. So that's the work in progress, but hopefully we'll have something to report back on that soon. So I think this is the sort of final summary now of the whole presentation. So hopefully you found it interesting. Yeah, FTorch allows for the use of ML with traditional numerical models. It accounts for language interoperation, so providing a solution for scientists implementing Torch models in Fortran. It's designed for both computational and developer efficiency, as Jack was saying before. So as well as saving you computational cost, it's also hopefully saving you time. And it's helped to deliver science and climate research and beyond. So there's lots of examples of that. And it's been built into the community Earth system model. And then towards the end there, I just talked about some recent and ongoing work exploring online training. So we'd be really interested to hear if anybody would be interested in using FTorch, and if anybody has any sort of potential use cases for this new functionality. So yeah, thank you very much for listening.